So, good morning to everybody, the present people, and also the people which is connecting to us. I think we have already about 50% or something that is additional somewhere. So I should say that it's not bad, the audience that we have local, but also a lot of people is around. So it's a great pleasure for me to have the opportunity to introduce Dr. Kasper Moth-Poulsen. So he's, as you know, a new ICREA research professor who has been integrated in ICMAB very recently. And so I should be the first to introduce him, saying that thank you very much for choosing ICMAB to develop your future scientific career. Now I will make a short summary of his scientific academic career up to now, who is very strong and very wide developed, but I think that the choice of moving from North Europe to South Europe has been really a big decision, I guess, for himself and also for the whole family. I have here a significant part of the family. And so for sure, I'm sure that you will enjoy this country, this city, which is very open and is very happy to receive people like you. So Kasper is an organic chemist coming from the University of Copenhagen, where he was first preparing the PhD and his license. Then he moved as a postdoc to the College of Chemistry in Berkeley. And after this stay in the States, he was recruited in the Chalmers University of Technology, where he started as a assistant professor. Then he was subsequently promoted to associate professor and full professor in 2019. And since 2020, Kasper was the head of the division of the applied chemistry of Chalmers. So in 2021, he decided to come and he was elected as a ICREA research professor. During his scientific life, he has made a lot of different things, and so he has received many awards. And I would just mention that he's editor of the journal Materials Chemistry C and Materials Advances. He has received many major grants, like the starting and consolidator grants from ERC, but also several of the Royal Swedish Academy of Science and different prizes, the Swedish Chemical Society, and Bergsäck from the Royal Swedish Academy of Science. He's a fellow of the Royal Society of Chemistry and the Royal Swedish Academy of Engineering Science. He has started several startups and spin-out companies. And he's also been selected as a member of the Royal Swedish Academy of Engineering Science just when he was already here. So congratulations for that. He will be integrated in the Institute in the Department of the Smart Molecular and Inorganic and Hybrid Materials, and he will start a new research group in sustainable molecular systems. So thank you very much for coming. I'm sure that you already know a lot of people at the Institute, but we'll do our best that you feel at home.
Thank you very much. It's a great pleasure to be here, and thank you for welcoming me and being so kind, all of you. I'll try to give in this presentation an overview of some of the things I've been working with for the last 10 years or so. So it will be a little bit of a Frankenstein presentation. I will excuse in advance for that. But it's because I see that there are so many possible overlaps or collaborations between different researchers here, and I want to show what we have done in the past in different areas. Yes, so the talk is officially called Solar Thermal Management Materials. It's reflecting the research focus that we have now, but we will also talk about nanomaterials, photon up conversion, and other things during this presentation. So the first motivation for the first part of the talk is that we have a lot of pollution in different places, even in Sweden, where it's not so dense populated as here. It's expected that 7,600 people die too early each year due to air pollution. So on average in Europe, it's 800,000 people, and we on average lose 2 years of our lives. And likely it's worse in Barcelona because it's a more dense city. So luckily, we are working with changing that. We are going away from burning things and into a more sustainable energy production. But this is only producing electricity, and we have to be able to store the energy for when the sun doesn't shine and the wind doesn't blow. And this with electricity is also important to remember that if you look at the European end use of energy, 48% is going into heating something, 25% to transportation, and 25% to power of different types. So it's really interesting to consider how we are going to heat something without burning something. And that is sort of the theme of my work. Most of this is coming from fossil fuels, and wood and coal and gas are of course very relevant, especially given the current world situation. So we have to think about how to produce heat without burning something. So how can we store energy? How can we store chemical energy? Of course, we can plant a forest. I mean, that has worked for billions of years. We can try to work with photo-induced water splitting, artificial photosynthesis. But I'm going to introduce to you a concept that is much less explored. We call it molecular solar thermal energy storage. And all these include some kind of exchange of materials with the surroundings. So you shine light on something, some chemical is formed, later you convert it back and burn it and reform the original materials. Where here, there are no exchange of materials, it's only photons in and heat out, and no materials, it's a closed cycle, no materials exchange with the surroundings. So this is how we, in a schematic way, envision the system. We have a parent molecule, we shine light on it, we form a photoisomer that is stable over time, and then later we can release that energy as heat and recover the parent molecule. So this has a potential advantages. It's a closed system. It can have very high energy densities. We can store energy for long term without having to have any insulation material. And we don't need any solar concentrator to attain higher temperatures because this is a chemical transformation. I will show you later what that means. So this is all great, but the only problem is that there exists no system that can do this really well. So that is, of course, the theme of our work, is to try to do that. So different systems have been explored. What we will hear mostly about today is called the Norbornadiene quadricyclane system. It looks like this. You have this cyclic structure here that can form a strained quadricyclane and can go back and release heat. There also exist other systems that people are exploring, azobenzenes or dihydroazolenes, that can also do similar things using different mechanisms. But our focus has been on this one due to different advantages that we think this system has. So if we look at from a sort of schematic reaction coordinate perspective, then we have a starting point here. We absorb light, sit on an excited energy surface, and then we fall down on a higher energy point here, where there's a barrier for back conversion. And then later we can switch back and release the storage energy. So our goal here is to maximize the storage energy. Actually, we want to minimize this to be able to absorb as many photons as possible, but also we want to keep this as high as possible, or high enough to make the molecules stay where we want them. So this requires a lot of compromises and thinking in molecular design, because all these demands or wishes for properties, they pull in different directions. At the same time, we want to keep the mass low so that we have a high energy density. So this is similar to battery research. You want to have as much energy in as little space as possible. So it's difficult to get all at the same time. So if we look at the system here, the core system, Norbornadiene, it stores about 1 megajoule per kilogram and can release it as heat. But the problem is it only absorbs in the UV and the efficiency of this conversion is only about 5%. So we need to optimize the photochemistry, the energy storage property, the heat release, and also how we make it so that we can make it at scale, cheap, and from readily available starting materials. So if we reformulate the targets and do a little bit of assessments behind this, we need to have an absorption onset at least up to 600 nanometer. We want to have a long storage time. We call it T-half, the half-life, the time it takes until half of the molecules have released the energy. Should be maybe weeks or months or years. We want to be a light molecule so we can make it in a cheap way, and it has at least 300 kilojoules per kilogram of energy density. This is some of the design goals. And when we started, the original system had been made, and also attempts to make all this work and commercialize it was made in Japan in the 80s with a donor-donor acceptor system with an unusual through space coupling here, so-called homoconjugation, where you can imagine the pi orbitals pointing towards each other here. So even though they're not formally connected, there's electronic communication between the donor and acceptor end of this molecule. So the way we work is that we typically start with some idea. Maybe we are supported by some computations. It's not everything that can be calculated. Then we make the material. Then we characterize it, absorption, quantum yield, stability, and so on. And then finally, what is maybe a little bit unusual is our group also do different test devices to sort of show this is what it can do. Or this is what it can do. Even though we are very early in development, we want to show or figure out how we can use the materials. So first, the absorption onset. This is a solar spectrum, and these are absorption of different molecules we have made, and the QC on unsubstituted Norbornadiene is down here. It doesn't absorb anything in the visible spectrum. So we have to do something about it. And we had the original system, we had this system, and we decided to make systems that look like this, where the donor and acceptor is sitting on the same side in order to make it lighter. You can imagine that you make a smaller molecules then, but also we have the double bond here that ensures electronic communication. When we form the quadricyclane, this is broken, and this means that we get a big change in color between the two forms, which is exactly what we want. So this is where the molecular design comes from. So this is the first series we made back in 2013 by Victor, who is now assistant professor in Uppsala and later did a postdoc in Cambridge. He's my first PhD student. He designed these series with donors and acceptors like this. And this redshifted the absorption a lot and improved the quantum yield a lot. But so since the molecule gained weight, also the energy density got substantially lower, and also the lifetime, how long time it could store the energy, gets substantially lower. So later, Maria came and made a new series where the acceptor unit was a very small cyano group. Through developing some synthesis, it's like this. I would almost claim that you cannot make any new materials without developing some new synthesis. So each new series of molecules have been made through some kind of methodological breakthrough or development where we have developed something. So I will not talk so much about synthesis today, but behind every new series of molecule, there is something that was not possible before that we achieved, and then we could make this series. So there's a lot of machinery behind these papers. This is just one example where we developed a new, more successful way to make this kind of compounds without using too toxic materials. So we made them, and they had a good color, more extended absorption into at least 450 nanometer. But you also see that the half-life, these molecules can only store the energy for a few hours. So if we look at the energy density, this one has about 400 kilojoules per kilogram, and this one 600 kilojoules per kilogram, so about 0.6 megajoule. So this we can measure by DSC like this. And this is more than our original targets. It's a factor of 2, actually. So improved storage time, improved energy density, but this is not so good. Also, it's a very robust system. You can cycle it for here 125 cycles almost without degradation. So it's actually photo switches that works really well. And this is something that when we started working with the Norbornadiene system, people always said, don't work with that. It's breaking apart, it's unstable, it's not robust. But with engineering and improving the system, it actually, you can do something like this that very few other photo switches can do. Going from absorption of 1 to 0.1 at one wavelength is not so usual. It's quite unusual, it's quite unique. You can see it also here from colored to completely transparent. So this is one of the special things of the system. But the half-life is not good. So there's a problem there. If we go back and look at the landscape here, we want to lower this absorption, lower the homolumo gap in order to absorb more photons. But the problem is that the orbitals that are involved, this is the HOMO and the LUMO, and this is the HOMO of the LUMO of the QC. There is some kind of intersystem crossing, and the barrier is sort of related to the crossing point of these two lines. So if you bring this down, the barrier will also go down. And this is opposite to what we want. So if you look at all the molecules we had made, they are lying here. They're following more or less this trend that if we increase the onset of absorption, bring down the HOMO-LUMO, then the back conversion barrier goes down. If we have not so much absorption, then the barrier goes up. And we want to be out here. We want to have a good absorption and a big barrier. How can we do that? So the first idea was to couple several switches together. So if we do this, then first we have a long conjugated system here with a low barrier. But then if we switch one of them, we will have a smaller system left with a bigger HOMO-LUMO gap and therefore a higher barrier. So this was a first design concept that we try to use to approach this problem. And the absorption onsets are very good. You have a very big shift in color here. These are the molecules. And it actually works, this concept. If you switch the first one, it has 7 minutes from this barrier. But if you switch the second one, it locks in and stays up here for 3 days. And the other one, 2 and 7 and 10 days. The other big advantage is that the donor system is now shared between 2 different molecules, which means that the weight of the molecule is much lower and the energy density goes up to about 1 megajoule per kilogram. So this is another effect of this design. So it works, high densities and some improvement in the storage time, but still not really great. So now comes something that we did not plan for. Sometimes the first idea here was something we had thought out and went to the lab, we had made it. This other study was not like that. So here, these two postdocs, Anne from Copenhagen and Marty from Australia, they had made a series of compounds. These are all substituents sitting up here. And yeah, I asked them, is there anything with this? What should we do? Should we publish it or not? There's nothing special, but okay, let's measure everything because there's quite a lot of molecules here. And then they started measuring the storage time. And then this one had 0.2 days, so this was the normal. But the other one had 22 days, so 100 times more. And that's just one difference in the attachments place. It's almost the same molecule. This one had 6 years, 7 years, 8 years, and 18 years. And each of these are highlighted here are between 100 and 300 times longer storage time than the similar isomer, like this one versus this one versus this one versus this one. So it's about a factor of 100 to 300. So what is going on? It is actually related to the rotation around this bond here. Now I don't think I have the full, no, I didn't show that, unfortunately. So this is about a rotation of this. So when you form the quadricyclane, it's a little bit more compact. You have more rotation here, and therefore it cannot go back through the same energy landscape. It's suddenly sitting in a conformation that is not allowed you to go back. So basically we are using the entropy to put it into a place where the barrier to go back is much higher. So it can go back, but it's just delayed by a factor of 100 to 300. And this became the top 3 most shared and read paper of the chemistry of European journal historically. So since they started measuring this. Then in another more recent study, we wanted to explore what if we add another carbon up here. So instead of NBD, we have EOD. So there's an extra carbon up here. What does this mean? The first thing it means is that this is a terrible molecule. So it means that it can do rate-reduced alder and form aromatic species. And this is, of course, not what you want. You spend a lot of time making your molecule, and then it falls apart. So for a long time, Maria, who is here, she was struggling with the synthesis just to make these compounds. It was not a fun project. But then in the end, she found out that she could make this acetylene and form this species here, and at a fairly low temperature at 60 degrees. And then from this one, again at 60 degrees, you could do Suzuki cross couplings to form a number of new molecules. So by finding a low temperature route with a very reactive acetylene here, then she could get the targeted molecules. And they were actually fairly robust. She could do 600 cycles with almost no degradation. And the interesting part here is that there is some extra strain up in the methylene groups up here, because they are forced to sit and frustrate each other. And therefore, the energy storage energy is about 76% higher than in the previous molecules. So it really could be a way to really enhance the storage energy in these systems. Okay, so now we had the original literature, and we had made several generations of molecules, and we had improved the energy storage density. We have fixed the storage time with different designs. So now we would like to show that we could use it for something, that we could heat something or get the heat out. Until now, it was just small measurements on a very small scale in a differential scanning calorimeter. So what could we do about this? How can we build small demonstrations that shows that it actually works? The first experiment was related to the problem, motivated by the problem that these molecules only absorb in the blue end of the spectrum. So there's a lot of photons above 450 nanometers. So we decided to use that these materials are transparent, and then have a water heating system underneath and create a little device like that. So in this small device, there's a top layer with a molecular solar thermal system and a lower layer with water. And therefore, the photons come in, 1.1% of the energy is stored, and 80% is then going into the water heating. So the combined system has about 80% efficiency of solar energy capture. Later, we sort of developed the idea, and a little bit like a multi-junction solar cell, we made several molecular species under each other, each optimized, sort of optimized for different wavelengths. This is the first conceptual paper to do this, and we have estimated that this can lead to maximal performance of this type of systems with up to 20% if you have fully optimized systems. In reality, we are far from that. Maybe we capture 0.5% of the incoming energy of the sun in these current systems. So we are really in the early days of developing this. And these are the structures that we used. These are collaboration with the Mogens in Copenhagen and Kimisuka in Japan, and then our group with that one. We've also built the outdoor test facilities here in Sweden on a sunny day. Shihang and Anna made this. Anna is now a lecturer at the University College in London, and Shihang is still a postdoc in my group. But they made this outdoor test device. So then now we can capture the energy. We have made different molecules that can store it, but we have not seen any heat release yet. So the next thing that becomes apparent is that if you want to heat something, it matters how heavy the thing you want to heat is. So if you have a very cool molecule dissolved in a lot of solvent, then the molecule cannot heat much. It's basic physics, and you have here the storage energy of the molecule and the mass of the molecule, but you need the heat capacity of the solvent, and the mass of the solvent is a big factor here. So the first molecule we wanted to use could only be dissolved in 34 grams per liter, and that will not give you much. So we had to go back and design molecules that were more soluble, and luckily this one could dissolve 300 grams per liter, 1.5 molar. So this was at least an improvement. We now have molecules that can be dissolved in any concentrations, but that is future things. But this was the first one. This should give us a heat gradient of 65 degrees, theoretically, if there was no heat losses. So this is our first device. You have the molecule solution coming in here, a spectrometer, thermocouple measuring the temperature before and after, a small catalyst, and then the molecules come out. But this is very small. This is like 1 millimeter by 5 millimeter. So there's very much heat losses here as well. So this doesn't work so well. So next generation was inside a vacuum chamber here, 10 to the minus 6 millibar. And now, for the first time, we could see a temperature increase when we pumped in our molecules. This is a temperature difference over the catalyst. It goes up to 50 degrees. And with a little bit of tweaking and adjusting the concentration, we could get 63 degrees, which is the gradient, which is current world record in this type of work. And you can see the relation between concentration and temperature. The black line is the theoretical without heat losses, and the blue and red are actual experiments. So in this system, it's very well insulated, so we don't lose so much heat. Then we continue to work on this, and this is a next molecule with very small changes here. The most important difference is that now you have very low absorbance of the quadricyclane. So you go from fully colored to fully transparent. And this can be also cycled for many cycles, and even going over a catalyst and being reused for more than 50 cycles without degradation. So we're really starting to have a system now that we can capture energy, store it, release it on demand, and cycle it again. This is not trivial to have that when you're trying to develop a fully new system. And what we then did was to combine it with a very efficient thermoelectric generator developed in Shanghai Jiaotong University by Jerry Hu. And then we could store the energy in molecules in Sweden, send them to Shanghai, release the energy, and generate electricity on demand. This paper is being published on Wednesday, and we expect it to also be featured in the Swedish national TV on Wednesday, associated with the release of the paper. So what more can we do? Another idea is to see if we could integrate this into windows, because we have a lot of heat during the day, a lot of sunlight, and often our offices get too hot. And then during the night it gets cold and maybe too cold. Could we do something to level out this daily variation in temperature? So the typical variation is the middle of the day, it's really, really hot. During the night it's cold. But we want to have a comfortable temperature around 21 degrees in our offices, right? And to fix this, we often have different blinds. But then a blind is not a window, right? It's not transparent. So what we want to have is a window that is transparent, but still regulates the temperature so it doesn't get too hot during the day. And that is what we are trying to do with our molecules. So this is the first example. This is a next generation system that captures about 3.8 of the solar energy. It's yellow first, but when you turn the light on, it becomes fully transparent. So this is the first coding. Here's a little video of. And when you take it out in the sunlight, it becomes fully transparent. We have later worked more with it and estimated how much energy we're talking about, how much is stored, how much is released. And and trying to play with the sort of thermodynamics and physics of this to create efficient windows. This is also the basic idea of our startup company, Solaris, led by Anna Hoffman, that is trying to commercialize or develop more larger devices like this. In another project, we are the most solar project is an EU project. We're trying to scale this and make it more efficient, building larger scale systems using this time molecules to really be able to heat something. The small micro devices I showed you was a few watts, and now we're going to go to a few hundred watts. So still very small, but going little by little forward towards maybe future applications. This is how it should look. Another very recent development that is to try to couple the energy storage with a phase change behavior, because the phase change systems, they absorb energy and then release it later when it gets cold. So it's a thermal regulating system that they need a heat gradient to work, whereas our system, they need light, and then the warmer it gets, the more energy comes out. So the two systems have different characteristics. The idea here is to combine them. And this way you get a photo-controlled phase transition. You can get that, and you can also enhance how much energy you store. So this paper was close to be the first example of this, but due to a lengthy publication process, we became second together with our collaborators in China. So they engineered different R groups in order to optimize the melting points of these materials. And what we could do was, this is how it looks. It goes from crystalline to liquid and back again, and everything can be controlled by photons in this case. And this is an example of a small coating where you have it here, and then you shine light on it, and then it starts to heat up, and then after a few minutes, it's cooling down again. So the power density is up to 3,000 watts per kilogram, which is quite significant. I mean, you basically shine a little light on it, and then it triggers a cascade of energy coming out of the system. It can be used to defrost a surface. So here is a coating that has been charged and put in the freezer, and it looks like this. And then you shine light on it, a little triggering, and then it melts the ice. So it's a sort of a automatic defrosting surface concept. It could maybe, with future development, be used to defrost the window of a car. It's not happening so often here, I know that, but maybe in other ends of the world. So this is the summary of our most devices. We have done solar capture devices, we have done heat release devices, and lately also heat to power generation. So what more can we do? What more have we done? And now we're going to switch to a little bit different topic, because if we look at all these solar capture processes, they all have the same problem. That is that they have to match the color of light coming from the sun. And this is not an easy task. The sun is as the sun is in general. So none of these processes efficiently use the full solar spectrum. So what we are trying to do, so what we can try to do is we can try to make the processes absorb more sunlight. That's what people who work with solar cells often do. But what we are trying to do in our project here is to change the color of the sun. What if we could change the sun's color locally? Then maybe these processes would be more efficient. So how can you do that? And so this is the typical absorption from our molecule, and this is the photons you really would like to use. But the problem is they have too low energy. So we need to change the energy of the photons to go in here. So basically what we are building, we have the same system as I showed you before, the molecular solar thermal system here. But then the light that is not absorbed is going down here and being upconverted to blue light that can then be used up here. So how can you do that? because normally when you shine light on a material, either light is absorbed and thermalized to heat, or it's sent out as photons again as fluorescence. And these are lower energy than what comes in, right? That's the basic laws of thermodynamics. You cannot create energy, you cannot do that. But what we want is this. We want the light to be blue. So how can this be done? You see an example here. So this is actually working. This is a green light coming in, blue light coming out. So what we're doing is we're combining photons in special materials, and the materials we're working with are capable of doing triplet annihilation photon upconversion. So what is that? You have a molecule that's a sensitizer. It absorbs light. It creates a singlet. It's spin flipped into a triplet, so it can stay there for a long time. Then the triplet swims around in the molecule, and it meets a so-called annihilator molecule and transfers the triplet energy. It's a triplet energy transfer. So now we have a triplet sitting on an annihilator here. Then you can do the same for two other molecules. And now we have two triplets, and the magic is then that when they meet, one is relaxing back to the original, and the other one is going to an excited singlet state from which it can send out a photon. So through this complicated scheme, we have started with green photons, two of them. We have gone through several steps, and out came a blue photon in the end. So when we started with this years ago, this did not work really well. It's a lot of things can go wrong. A lot of molecules have to meet. A lot of energy levels have to match, and everything can be destroyed by oxygen. So there's like problems all over the map. But this is how it typically looks. And I'll just show you a few examples of what we have done. This is another way of looking at it. So if you see that you have two photons and they're making the singlets, the triplet energy transfer, and then you form the singlet on one of them, and then you get the blue photon out. And this is the fruit fly of this type of work. This is a sensitizer, the annihilator, diphenyl anthracene. And in our definition, if you use two photons to generate one, it's 50% efficiency. Half of the field, they like to think 100% sounds better. So they multiply the results with factor of 2. And that one has to be careful when you compare different research papers. We always stick to the UPAC definition of fluorescence. That means that number of photons in, out divided by the total number of photons, that's the maximal efficiency. But there's a lot of discussion around this. But, this is the logical way we think. Okay, so this is our first example of using this to drive a chemical reaction. So we have here the sensitizer, the molecule storage system is looking a little bit different here, and the emitter, you see an overlap between the two. And this is how it looked. It's very, yeah, this is the device with the microfluidic channels. This is a filter, all dipped in water to not heat up. This is the best we could do at the time with state-of-the-art materials combination at the time. But we could improve the energy storage efficiency by 130% by using the upconversion system. But since then, a lot of things have happened. Here you have a more modern combination where we try to solve. I mean, now we're stepping 7 years later. So now there's the things that didn't work here was that system was in solution. It's not really practical for solar cells. You want something solid, right? This system is extremely susceptible to oxygen. It will be quenched. So that also has to be solved. And lastly, it has to be robust over longer periods of time. 7 years later, we have that. We have now more or less this. These are the new synthesizers. They're looking more or less the same. This is the annihilator looking more or less the same, but it's now in water. And the magic trick is to combine it with some surfactants and some gelatin to make it solid and biocompatible, and have this as an oxygen blocking matrix. So in this way, we can put all the organic reagents into a water gel sub thing that could in principle be applied to a solar cell or other things and change the color of the light locally. And this is how it looks. It's a little bit yellow, and out comes the blue light. So this is actually a current world record in solid state upconversion systems in this wavelength range, going all the way from the IR into the blue. And then, of course, if you have a solar cell that is absorbing here, it will not work. So we have to go a little bit further, but the principle is there. What is also a new thing that we start to think about is when we make new material, if we are successful and they have to be used in the future, there also have to be a way to recycle the material or reform them and make sure that they're not just being used once. So here in this paper, we also have a scheme for recycling all the chromophores and putting them back into a new device with the same performance. So if the device is end of use, you can collect it, wash it up, and remake it again. Okay, so maybe some of you here are old enough to have seen the movie Star Wars: A New Hope. It was come out 1 year before I was born, but I saw these screens in the back. How are they made? Well, they're not really, they're quite static in the movie, so they didn't really work. There was no moving parts, right? But how could we make one like that? One idea that we had was to, what if these were a film on glass with that was where you had a IR laser from the backside that shines that's invisible light, IR light, onto here, and then upconverted into blue emission that you can see with your eyes. Then we would have the Star Wars screens, right? So this we decided we want to build. So this work, we combined old technology. A lot of these liquid crystalline display concepts have actually, Chalmers have been a big actor in that area 15, 20 years ago. And we teamed up with a professor who had built LCDs for many years. And LCD works that if you have two transparent, one transparent electrode and a non-transparent, and then you can have some alignment layers, and then when you put a bias on here, all the molecules switch direction. They go in the same, the dipoles of the molecule goes with the electric field. So what we did was to incorporate this into a matrix, these components into a matrix from a liquid crystalline display. And this one had also a dipole. So this was the one working the best. So here we have a switching of upconverted light going in a certain direction, switching together with LCD. So basically this could be 1 pixel of our Star Wars display in the future. Yeah, this is the last development from our group here. This is a UV upconverting system, visible to UV, operating at 17%. So during 10 years, the efficiencies of these systems have gone from 0 in this range, but very low percentages in many ways, and up to 17%, which is fairly close to 50%. That is absolute theoretical max, but there are other limitations that I cannot go into. These are actually breaking some of the original theoretical limits of what is possible. So these are summary of our upconversion materials. So for the last 10 minutes or so, I just want to show you a final little story about our nanomaterials and molecular electronics work that we have done. So this story starts with a paper from Alivesator's group at the UC Berkeley, where they nanofabricated a small gold prism and a palladium nanoparticle. And by doing this, they could use the color of the gold would change. It's a plasmonic property change if something happens to the palladium. And that something could be that hydrogen comes near and the palladium expands. But this is done in the clean room. It has been a challenging task to nanofabricate this in a nanofabrication lab. So what we wanted to do was to make this through synthesis, because synthesis is scalable. It can be done in a normal chemistry lab. So we want to make something like this with self-assembly. A gold particle together with a palladium particle. How can you do this? plasmatic sensing unit, a catalytic unit. So here, Tina, one of my first PhD students, she developed a way to make a negatively charged particle, purify it, and combine it with a positive charged one. Normally, if you do this, you will get everything will precipitate. You know, everything will drop out of the solution because you have, it's like a nano version of rock salt, sodium chloride, right? You have two opposite charges, it will just precipitate. So she mapped out when this precipitation would happen with different surfactants for the citrate stabilized particles and for the CTAP stabilized particles. She mapped out when they were stable, when they were precipitating. And when you overlay these two maps, you see a very small window. If you zoom in here, both of the particles should be able to exist together without crashing out. So, I mean, this was also a silly project that I made up, right? Because this would be, when you see this, it should look like it's going to be impossible. There's no window. But actually, when you start to work with it, the window is there. And this is what we then did. So with this, we could produce a lot of different particle combinations. Basically, we are starting to form molecules made out of particles. These are small plasmonic molecules synthesized in this way with different materials combinations. So here are some other examples. These are palladium octahedra with a gold particle, palladium cube, and another palladium structure synthesized in this way. And the cool thing is that this works as a sensor also. We can learn from single molecule experiments the thermodynamics of palladium uptake of different sizes and shapes of particles, studying one particle at a time. Later, we wanted to scale this to make sensors that were a little bit more bulk, putting the particles into polymers. And here, Anna Peccari, together with Victor Sebastian here from Spain, developed a synthetic route for palladium cubes in flow chemistry. I could make them many different sizes and shapes. Here, palladium platinum core shell particles. They could be incorporated into a polymer matrix, and in a series of papers, we have optimized this. The idea is to combine plasmonic particles that easily get disturbed by different surfactants or impurities in surroundings with a polymer that shields them, and making things that we can 3D print. So we have developed a lot of different polymers and materials combinations in order to be able to make some of the fastest hydrogen sensors in the world based on these materials combinations. Also resulted in developing of these methods resulted in the startup formation of this company, Nanoscientifica. This now have 2 employees in Gothenburg, Robson and Sarah, who are both former postdocs in my group. The last little story, last 5 minutes, is about single molecule electronics, where some people predicted that the future computers will be on the molecular scale. But the problem is, how can we make these computers? I mean, this is one of the old original papers. We have the vacuum tube, the transistor, the integrated circuit, and maybe one day the molecule. So how can we do that? And our idea here is that we want to take a solution of molecules and nanoparticles and put them together with an electronic circuit and make something like this. So we want to isolate first the molecule with the nanoparticle and then assemble the nanoparticle onto the electrodes. So in order to do this, a lot of different surface chemistry and nanoparticle control had to be developed. And I just give you a little accelerated 5-minute version of this. So basically what we do is that we take an excess of particles together with some molecular electronic components. Then we separate them through centrifugation and form the dimers like this. This is how it's separated with a special type of centrifugation with a special density of the solution here. And then the next critical step becomes how to take the single molecules and put them onto the electrodes. And this took a long time, but here's an example of how the winning design of electrodes were. So this is small sort of hands like this. And if you dip this into a solution of nanoparticles and you control the surface chemistry and all that, then you can get the particles to land onto the electrodes like this with about 34% device yield. This is another way how it could look. You have there's a lot of materials, different materials that are needed to make this work to get the right surface charge. And this is the final examples of devices where you have a dimer here with a single molecule in between, and you can actually do measurements on it. We spent 6 years on this, and I'm not sure I will recommend you to try the same. The device yield was not as high as we hoped for, but at least it worked sort of in the end. So we were very happy with that. What also came out was a new molecular electronic switch. This is again our Norbornadiene quadricyclane here in the middle, now with thiols in the end, so it can go between electrodes. And it's a very robust switch here. It's switched 120 times with light. This is some acquisition error. It's more than 99.998% yield per photoconversion, which is a quite good chemical reaction. But interestingly, when you put it into single molecular electronics measurement, you get an on-off ratio of about 6 between the two different states. And Gemma Solomon at the University of Copenhagen said that this was something called sigma interference. I'm not sure I fully understand what that means, but they claim that the currents are actually taking the long route here and not the shorter route during some kind of quantum interference in the molecular system. Later, something very interesting happened that further experiments showed that we could actually switch this using a bias only. So this is a two-way electronically controlled electrical switch. So with putting this in devices, putting a certain bias, we could force it into one form, and changing the bias, it could go back again. I'm not aware of other photo switches or switches like this that can do this. So this was a very big moment for us when we actually were able to control making a single molecule memristor in this paper. So this is a summary of our work on nanoparticles through the last 10 years or so, with developing ways to make nanoparticles and make plasmodic molecules in a controlled way, ways to isolate single molecules and put them on surfaces. And this was an examples of some of the work on molecular electronics that we have been doing. We have also been working with battery electrolytes and other materials, batteries, but I will leave that out today due to the interest of time. This work has also resulted in 3 startup companies, Nanoscientifica making nanoparticles, Solatis making functional coatings, and Conscience doing nanofabrication for academia and industry. In the future here at ICMAB, one of the goals is to continue this work playing with solar energy and ambient heat and storing it in a material and send it out later as upgraded heat or maybe power. And this is the theme of 2 of the projects that we're going to start now. We're currently recruiting people to the ERC Consolidator program and this EU project. So we're going to play with this landscape from liquid molecules into solid, switching them and back into this cycle here. What we're also going to do is to build an automated platform for molecular synthesis, because none of these new materials are possible without new methods. And the new methods, the new direction we are going here is that we want to accelerate how we make the molecules. So there will be, hopefully in a year from now, a robotic platform that integrates weighing, evaporation, UV-vis, chromatography, liquid handling, flow chemistry, and analysis, all in the same lab. And this platform will not only be controlled by robots, but also by humans. So when the robots doesn't work, we will be able to access it also. So it will be a platform that hopefully will accelerate how we can make molecules, and of course available to everyone here at the ICMAB. So I think it would be great to when this is working, and we're currently procuring different components of this. So we plan to work with the AI, designing the experiments, make the experiment, test it with inline spectroscopy, learning from it, and doing new experiments in sort of a human-free cycle here, so that we can really optimize and develop new materials at much faster than what we can do today. These are some of the collaborators of what I've showed today. People at Chalmers, Gothenburg, Shanghai, Kyushu in Japan, Copenhagen, Rioja, and Germany. And these are some of the companies that are sponsoring our work in different ways: ExxonMobil, Johnson Matthey, and HSB Living Lab. This is the current group members. Most of them are in Sweden, except for Clara, who is here at ICMAB. And these are past group members and the funding agencies. Thank you for your attention.
Yeah. So many things. I'm sure that it has been very inspiring for most of us. And so now the presentation is open for questions or comments of any of you as well. You are aware if other people is asking for that. So who is the first?
Maria?
Thank you very much for the talk. Wonderful. And thank you very much for being here. So I just have a curiosity. When you show the 2-thiophene and the 3-thiophene, and you show the different T1/2,
can you speak louder?
The 2-thiophene and the 3-thiophene, and the difference in time. Later on, you referred to the rotation of the benzene, but I didn't get it.
Now I cannot draw it for you so well here, and I should have brought in another slide that explained it better. Let me show you. Let me find it. Yes. It's coming.
That is just a change in the software. And
let me show you what it is. I'll try to explain what it is. It's coming up. It's a lot of too many slides. Oh, okay. Now it's this one. Yes. So this is the question is related to these two, and it is like if you imagine this is the double bond and this is the aromatic part. When it's sitting like this, it's conjugated. When it's sitting like this, it's non-conjugated. So when it's sitting in the one form of the molecule, it's like this. Then this other has switches, which allows this to rotate more freely. But the lowest part of the barrier, for going back, the barrier is in 3 dimensions. Normally we just draw it as one line, but if you have rotations, it becomes a 3-dimensional landscape. So the lowest point of the crossing point requires a certain geometry here, and all the others will have a higher point. So if you now are free to rotate, then you will only be in the lowest point more rarely, and therefore you cannot go back. So one of the difference here is a small spherical change. This one has the more spherical hindrance with the 2 hydrogens, where this only have 1. So therefore, the effect becomes more pronounced. So that is, it's not so evident here. I should remember to bring, you're not the first one asking this, and I should remember to put in the landscape calculations, because these are the ones that are sort of explaining that there's a difference in barrier depending on what conformation you are in.
Thank you. And the other one, it is in general with the NBT, because you show that you also have, with other materials, have proved to the reconversion of this material and to do it in the new, to use it, to reuse it. And I was wondering about the biocompatibilities or the studies in that direction.
That's a good question. We have done some initial toxicology studies where it showed that it was sort of okay, but we have not gone really far because the basics is to see if we can make it work and sort of from a fundamental point of view. But eventually, if this is going to be large scale, we have to study this also. But first, we are struggling with many technical challenges. And
you have a wonderful system. Thank you.
Yeah. So here we have another question from Pep.
Thanks for this. I think it's a great presentation. I'm not working on that, so I'm not sure that fully understood, but I think it was really an impressive presentation from my point of view. Now I would like to comment, to put a question, maybe it's a very simple question, on the most molecules that you described at the beginning.
Yeah.
So basically we shine light on a molecule, you go from one molecule to a different molecule, and you store energy there, and somehow this energy cannot be released because energy barrier to go to the initial state. But then later on, you mentioned you can release the energy on demand.
Okay.
How can it be?
Okay, good. So it's good, very good question. It's if we show it here, it was not fully clear from my talk. I realized that. So good. Thank you for asking it. So there are basically at least 3 different ways of doing this. So then the simplest way is you shine light on it, it falls down here. And then the molecule is not sitting still, there will be some vibration, and some of them will jump here. This is the natural half-life. There's no control. The second one is catalysis. So in some of the experiments with the heat release devices, we had a catalyst that we had explored and identified materials that could catalyze this. Then we also have some of them we can photoconvert. So some of them have an absorption here that you can use to make them go back again. So one wavelength take you in one direction, one wavelength to the other. Then you have an external control. And the last one is that some of them are electrocatalytically converted. So you can have an electrode and you apply a bias and then the energy comes out. So there are several ways of doing this, and I did not have time to present all of them, but these are the different handles. And it's not all the molecules that can do everything. Some of them are tailored specifically for it. And for example, the NBD system, we made the first example of NBDs that could be photo switched in 2 directions with visible light. So this was not known. I mean, this path was not known, not done so much before we did that.
More questions? Just a moment. Take this.
Connected to that, for the window application, what you like is to have a system that during the day, so you convert to this form that stores the energy, and then it automatically transforms to the other initial form, releasing heat in the 12-hour scale or something like that.
Exactly that.
Okay.
So for that, we will not use these very long half-lives. We will use molecules that have a half-life of 4 to 12 hours. And that is what we, in this paper that comes here, somewhere it's there. Here, we are starting to figure out what the ideal should be, how should it behave, and what will the consequences be. So this is very relevant, and it's not so simple to answer, and it's not so simple to make systems where these effects are very pronounced. So you can see here, these are a few watts that is coming out and a few watts that is taking out of the spectrum, but the sun comes with 1,000 watts, right? So these are small energies compared to the full spectrum. at this stage.
Thank you. Other questions? Sorry.
Not only electronic effects, also crystal packing can be important for the molecules,
Yes.
I suspect.
Definitely, definitely. These are one of the themes that we are going to play a lot with, where we are going to try to engineer the phase change. It's going to be a core part of the project is to try to engineer this and use it to our advantage. And that is going to be one of the themes of the coming 5 years, is to engineer this. So we have just seen the first examples of photoswitch systems that can both capture energy and do the phase change. But I think the next years we'll have a lot of examples, not only from our group, but others, on how to engineer this, try to understand this, and try to figure out how to use it in the best possible way. Definitely. Yeah.
Thank you.
Now a question on the chat. And you.
Well, my question is very simple. It's regarding the up conversion process.
Yeah.
If you have a great dependence on the light in the incident light power.
Sorry, can you please repeat it?
During the up.
Yeah, good. The receiving light power. Yes,
Yes.
that's correct. I did not talk so much about the details, but that's true that it's depending a lot on the intensity of incoming light, and often you have so-called quadratic dependence. That's correct. Yes, and the challenge is to develop systems that works even with sunlight irradiation. And in the beginning, it was not possible to do really well with sunlight. So therefore, that's a very powerful halogen lamp here. That's why everything is in water. So sorry, what is the question again? Yeah.
No, you're looking for applications with sunlight. So
Yeah.
I was asking about what the amount of energy power that you, or the amount of incident light power that you need in order to get the up conversion.
Yeah, I have to check specifically with some of our systems, but some of the best systems in the field now, they can actually work with the normal sunlight. So they can work quite efficient with normal sunlight, but efficiency normally increase with higher light intensity. So this is still something to work with. But basically, if you have very long triplet lifetimes and you have a very optimized system, then the low light intensity is not so much of a problem. So I think that's where, more or less, where we are getting now in the research area, is that it starts to become possible to do things even with normal sunlight.
Thank you.
Yeah, thank you, Kasper. So yeah, thanks for this beautiful talk and showing how molecules are so interesting and how much you can do with that. So related to the previous question, so you showed this T-half very long, like 22 years. So do you know what happens when they are in solid? Is there a big difference? Because I guess you optimize it in solution, but also maybe they behave really different once they are in solid.
This is a very good question, and depends a lot on the system. So you can have solvent effects, or you can have different polymer matrix effects. And these are definitely there. And this is something we have to be aware of, that things may change. This is especially the case if you're working with the atobenzenes, where you have a very big conformational change. It's difficult for that to happen in the solid state.
Yes, this is something you don't have.
And that is actually, I didn't say that so much, but for that system with the liquid and melting here, is actually the liquefying is happening from the surface. So it has challenges because of, no, I missed it. Okay, it has challenges because of this. The Norbornadiene just have very small changes. So many of the properties are almost the same in solid and liquid, but there the challenge is in the reactivity to the neighboring molecule. So we have challenges with the degradation if we have 100% Norbornadiene, because you have the radicals and you have double bonds, and they want to react with the next molecule, and then you get a polymer. and that is not what we want. So this is something we're currently working with, trying to fix. So there are several molecular systems that are candidates here, and they have different plus and deltas, we can say.
Yeah, really interesting. Thank you.
Any other question from the audience or from the website? No. So can you mention a little bit better what you showed about the preparation of the nanoparticles, which are perfect and so beautiful? This can be done in metallic nanoparticles.
Yes. So we have made
compositions.
Exactly. So there are two things here. One is how the particles are made. So these and many other examples of other materials components are made in what is called flow chemistry. So there instead of having a round bottom flask where you cook up things, you have tubes and pumps. And the difference is that in the flask, when you start the clock for making nanoparticles, you want everything to start at the same time. So you normally try to have a lot of steering or try to control when the reaction starts at some certain critical temperature. And that is how scientists working with nanoparticle synthesis in general try to do it. In the flow chemistry, you have the advantage of very high surface to volume ratio. That means heating and cooling and mixing is super efficient. So you have two small streams of material, then the clock starts when they meet in a very controlled way. And that is why all the particles get the same size, because the clock starts at the same time. Then you have to fine tune other parameters. You have other challenges with particles not growing on the walls, not getting stuck different places. But if you can resolve that, then you have this method. Then what materials? We have mostly been working with different noble metals and combinations. So gold, silver, platinum, palladium, copper, silver. But there's basically no limit to that. So that is why it's interesting. And the next level why it's interesting is that once you have a recipe, you can scale. So if you try to bake in a flask and you want to make in a reactor, the mixing and heating and cooling becomes different. If you can make it in flow and it works, you can just let the pumps run for longer time, and then you continue to produce. And this counts both for the molecules and the nanoparticles, that some of the things we are making now in flow, you make it on a normal milligram scale, but then next day someone comes and asks you for a kilogram, and then you have a problem normally. But not with these automated methods. Then you can go from milligram to hundreds of grams. It's just a question of buying more starting material and then press the start button. And that's a very big advantage because then you're not so often you're limited with the amount of molecules you can make, and not here to the same extent.
Good. Then in the robot system, you want to use the flow chemistry as well?
Yes, it's part of the robot system.
Combine
I did not disclose it here. We'll not have a humanoid robot. It will not. I'm sorry. we will not have them walking around like that. At least this is not the plan for now. It will be not looking like that. I did not want to show how it exactly looks, but you can see it later.
Okay. Yeah. No more questions. Anybody else wants to make any comment or not? So, okay, Kasper, it has been very nice to hear you and to see so many things in your head and so many plans for the future. So good luck, and hopefully we'll see in some time these realizations. Thank you very much again, and welcome to ICMAB.
Thank you very much. Thank you.